Have you been to Harbordale before, or is this your first time?
No, this is my first time.
First time. Okay. Have you settled down? Your place, everything?
Mostly, yeah.
Is it okay if I face the camera in the beginning on this side so that they can see you? I'll move things around. Hello, Alia. Oh, volume. Oh, what happened to volume? Can you speak again, Alia? Maybe. Can you guys hear me? Hear us? Mic. Hello?
Hello.
Hey, Jordan, can you hear me?
Yep, I can hear you.
Alia, can you hear us? Oh, probably. Alia cannot hear us. Or maybe she's talking, but she's muted actually. Yeah. Okay, probably. Hello, Michael. Michael, can you hear us?
Yes.
Hello, guys. So, there's a homework one that is due. August 25, Thursday. And I think earlier I might have said that I would prefer a hard copy. Let's make it D2L. I'll try to use the annotation on that. It's not the most convenient one, but I'll try to make it work for this purpose. We have a midterm one, which is September 10th, Thursday. This will be in class. Hey, what's this? Yeah, we moved around the tables.
Yeah, no worries.
Yeah, that was a confusion.
Yeah.
I was told not to move things around. Yeah. And remember that there are extra credit problems. I won't list this all the time, but it's expected that this is due every class. In fact, what I suggest is that even if there is nothing, just put in something and they're saying that there were no questions. It's just then every day I gave to give some points. So
Did you say that you were okay with receiving physical submissions?
for extra credit,
Extra credit, you want them to be online?
yeah, let it be
Got it.
online. If you have not done it today, this
I
time.
can submit it online.
Yeah,
I mean,
but
this-
it should allow you to submit. That's the thing.
Oh, I
think
see.
there's a due date.
I gotcha.
So send it by this one. Send it by email. But
Okay.
typically, I won't like it's just inconvenience.
Yeah,
I
gotcha.
have no issues, and if everyone starts doing it once and every time, it's just inconvenience. But this is a small class. I
Right.
don't think I mind it so much.
Okay.
But if this was a class of 50 students, probably
Right.
I'll probably say no.
But for homeworks, you said you.
Oh, so that is a change here. Yes, I did say that physical, but now that just to make it uniform,
Okay.
I'm trying to learn this on D2L. So I'm going to allow you or make you guys submit on D2L.
Okay.
Now the challenge there is that the annotation tool, that's I have to grade and preferably I would like to write something on that. That is not a continuous thing. So it basically connects a line. Wherever you end the line, it makes a straight line. So maybe I'm using it wrongly. So there's a challenge there. So if not, at least I will use text to write. I was
Sure.
trying this with your extra credit. I did write graded, good, and those kind of stuff. But preferably you would like to write an equation or something. So we'll manage somehow. So yeah, so the answer to the question is make it D12, but midterm will be in class anyway. So if that is not,
Okay.
if you guys think that that's really not helpful, just submit it and small class, no issues.
Sure.
Okay. Okay. I should also say that some of the things I taught in the first class that's useful also for E&M homework. So that was one of the reasons that I was trying to cover this at the same time, and most of you guys are there in both of these. Any general questions before I proceed on? Okay. So all of us are here. 1, 2, 3, 4, 5, 6. Yes. Okay. So we were working on index notation. Oops. Index. Notation. Readable? let me know if you guys need to do or do something. Okay, so we said a vector. So we so here is how we can say. So if you have a quantity that has 3 components, so this means I could be 1, 2, 3.
Excuse me, doctor.
Yes, please.
Can I ask a silly question?
Yeah.
Is my picture upside down or what? Or is it good upright?
No, you guys are all perfect. Yeah, at least on this.
Good.
Yeah.
I flipped the iPad. You know, I'm not sure what I'm looking like now. That's okay. Just to make sure.
Yeah, you guys look you're on a grid. Yeah.
Thank you.
On the side. And in the beginning, I tried to put the camera on the class side so that at least for a few minutes you could see each other.
All right.
So
Sorry for interrupting.
So there are 2 students here. I think now that we have this. Yeah, so.
Hi guys.
You're not there. Moses is not there. You're all there. Oh, no, that's the extreme it goes. Well, you can just say hello. So, it already fails, huh? Okay. Okay, great. Yeah, so I was saying we try to introduce index notation. So we are assuming that it is 3 dimensions. So I can run from 1 to 3. But the advantage, one of the reasonably trivial advantages is that most of what you do here doesn't really care for the dimensions. You can easily extend it further. But again, one of the trivial advantages in that. So this will be called, whenever it's 3 components, it's a vector. So that's tensor of rank 1. That's we said this is free index, right? So it's one free index. Again, we are assuming that we are in rectangular coordinates, or we have 3 orthogonal unit vectors in terms of which these are the components. So AI are components, right? Components of vector A. That's a understanding. And again, we are doing it at a user level. We're not really going into the conceptual level in that. If there are 2 indices, this is no more the same as the first quantity. This is a tensor of rank 2. So there is no way this can be the same as the other one. So this is, you can think of it as a matrix in very simple language, or an array, however you want to say it. If you're doing computers, you would use it as an array. Sometimes you call it a matrix, but technically it's a tensor of rank 2. And it can be generalized. And of course, there is A right here. If there is no index at all, that's a scale. Right? Tensor of rank 0 in that. Okay, so that's kind of what we are doing. We introduce, that's notational or terminology if you want. We introduced 2 special tensors. One is delta ij, that's Kronecker delta. Which is basically, if you think of it as a matrix, it's a unit matrix. And so it's a tensor of rank 2. And there is also a tensor of rank 3, which we like. That was called Levita sum. And we defined these quantities. We said a dot product between two vectors, A dotted with B, has this nice representation. Since it's a scalar, dot product is a scalar, we don't have to talk about indices, which index doesn't matter on the left hand side. So this is AI, EI. And remember, if there are two indices that are repeated, that means there is a sum acting on this. So implicitly, you have to imagine a sum over I running from 1 to 3. So that's the main idea. And that is also, in terms of Kronecker delta, you can write this as that actually leads to a simple trick, very almost all the time you can do this. If you have a quantity del ij bj, so this is first we can ask, is this a vector or a scalar or a tensor, or how many free indices does it have? Right? It has one free index, and this is repeated. So the main point is that this is always collapse the j's, and this is bi. That's primarily because Kronecker delta does not survive when I is not equal to j. So since Kronecker delta imposes I is equal to j, you can replace I with j. So when you replace I with j, so j becomes I. Right? And whenever this is the same, that's the one. So this is sort of, in the beginning, you have to verify that this is actually true, but very quickly you realize, oh, that's the that's a process you use all the time. So that's A dot B, and what about A cross B? A cross B is a vector now. So since you're talking about components, so that is the ith component of A cross B, right? So you talk about what is A cross B, and in terms of indices, this is ijk. So the ith component is I times jk, and this has a cyclic property and a symmetry property. So Levita has nice, interesting properties. In terms of that, we showed that this is dk, right? So that was that was a simple summary of that. But now we want to do more compound statements. Concerning these vector identities, and especially we want to introduce the gradient operator. But first, let's see some small identity related to relating the Levi-Civita symbol and the Kronecker delta. And it will be mostly motivated. I won't try to. One can actually verify it. That's the easiest thing to do. But notice that so we can talk about symmetry under interchange of indices. Right, so let's investigate that. And we learn that as far as Kronecker delta goes, you ask, what happens if you flip it? What happens if you flip it and you realize that it's the same, right? It's either 1 or a 0. And when you flip j or I, it doesn't change. So you say that this is symmetric. In I and j. So what the point is that if you swap I and j, that is the same, the matrix. So it's like saying if you have a diagonal matrix or a Hermitian matrix, that's or a symmetric matrix, right? That's what you say. The transpose of the matrix is the same as the matrix itself. So this is like taking the transpose of a matrix. Correct. Let's do the same thing in epsilon ijk, and let's ask what happens when you change J and K. So this is a J. And you can take a specific example and you would see that, oh, that's not correct. In fact, if you were to add these two, that's 0, so in fact there's a negative sign. So you would say this is antisymmetric in interchange of J and K. For that matter, I could have changed any of these two and it would have changed sign. So first let me write it this way. That's minus J I K. And I could also change to IK, right? So it's K, J, I. And all possible interchanges, it's minus 1. But what if I do this twice? Now I interchanged J and K, but next I do I and K, so that again changes sign. So this is minus 1 square K, I, J. So that's the antisymmetry property of so you would say, let me say it as simple as antisymmetric in all its indices. So by that when you mean that when you interchange them, what happens? There is another quantity that has the same property, and that's a determinant of a matrix. If you were to interchange the columns or rows of the determinant of a matrix, the determinant also changes sign. So you use that property and you can verify that if I were to multiply IJK, then LMN, before I write this on the right hand side, how many free indices there?
6.
6, correct? So there's no addition, so there are 6 free indices. How many components will it have?
A lot.
A lot, yeah. 3 raised to 6, right? 3 times 3 times. So this can 3 times 3 times 3 and 3 times 3. So 27 square, right? So that's a lot of components. That's very right. But all this, if you are to evaluate any one of them, so there is this nice little identity, and that's very useful. And that's I times L. So notice a connection between Lewis-Civita symbol and Kronecker coming in, or you can say that at least this product can be written in terms of Kronecker delta, and this is convenient. So this is N. And again, the pattern is obvious, it's very easy to remember, and you can always evaluate any component you want by putting in the, so if you put it on the left hand side, anything, you put the same thing on the right hand side. Right hand side is easy to evaluate. In fact, left hand side is also easy to evaluate if you know the definition of the symbol, and that's what it is. Often it is not necessary. This is really doesn't arise so much, but we will see where it comes in, especially the triple cross product. You will see this show. But let's once we have this 6th rank tensor of rank 6, right? You can collapse this now. So let's say, and again, I hope this is clear that by determinant I mean that I multiply this with determinant of the small quantity, so I'm not explicitly writing that. So there's a series of how many terms will it be? So 6, right? 6 terms with each one having a product of 3 Kronecker deltas. If I collapse one of these, and by collapse I mean well, the technical term for that is contract. So this is called contract. Call it contraction. And by contraction, I mean there's now a repeated index in there. So now what is this equal to? Is this a tensor of rank 1, 2, 3, 4? How many How many free indices?
There's one or two free indices, 4 free indices.
4 free indices, right? So now
3 times 3 times 3, you know, 8 times 3, 9 times 3, 27 times 3.
yes. So 81 components, right? But now it is actually easier to list them, and this will be useful. In fact, you should start. It's very easy to remember also. Now notice once I is gone, I have JK and MN. So notice what this is equal to. So this is JM and then KN. Notice how I'm writing. Order matters. J, M, K, N, and then swap it with a negative sign. So okay. It's almost immediate once you put this on the top one. It's almost immediate to verify that. So I started with a 6th rank tensor, contracted one of the indices. I'm left out with a 4th rank tensor. I contract again, right? Contraction again. And this time I do IJK and IJN. This is a tensor of which rank? How many free indices?
2.
2, right? 2 free indices. So that's kind of a matrix, correct? So that's, and that is equal to, so this time I just have to replace M with, so let's evaluate, right? Now it's small enough that actually, so M becomes J, so this is JJ, delta KN minus delta J, N is, so what I did was I substituted wherever there was an M, I substituted a J. What is this equal to? What is delta JJ?
1.
Try again. Don't forget the rules. I cannot write on this board, so let me do it here. What is delta JJ? Repeated index, remember that. Implicitly, there is something. 3, right? And why is that 3?
Oh, yeah, that's right.
Right?
Yeah, it's
So
the sum of 1 plus 1 plus 1.
Okay, don't forget that. So this is delta. There's a sum here, right? So it's tempting to forget that. So this is delta 1, 1 plus delta 2, 2 plus delta 3, 3, and that's 3, right? So yeah, I realize that it's tempting to think the other way, but it is 3. And usually you don't have such answers, right? What is delta of 3? Then of course usually it is 1 or 0, but understandable. Okay, so that's 3 times delta Kn. What about this? Now, remember your contraction rule. If I were to contract J and J, right, I can forget the J and replace either K with a, or this J with a N, or this N with a K. Is that clear? Remember, where was that? Okay, now try to insert N here. Remember the rule that whenever a Kronecker delta comes multiplying Bj, this is nothing but Bi. That's sort of a rule of contraction. Whenever a Kronecker delta comes in, it will survive, only the ith component will survive.
It's just del nk or del kn?
Exactly. So this will be, I can replace this, so this will be delta Kn. Right, very good. Right. Is that clear? That basically saying that you're multiplying an identity matrix multiplied by a vector is a vector itself. Right. If you think of it as a matrix, identity matrix multiplying multiplying a vector gives you back the vector itself, or in terms of components, you're saying that since the Kronecker delta survives only when I is equal to j, it picks out that particular component. So this is kind of an important step. That's the rule. If you want, eventually it becomes a rule, but that's in the beginning you have to realize why you do it. So that's 2 times delta Kn. Right? So the identity is 2 times delta Kn. Right? And you don't have to remember this. What I suggest is that remember this one. So, like this is, you will notice that you don't have to really remember. You will use it so often that you will tend to remember it after a while. So remember this. This one is sort of, it doesn't show up so often. This shows up a lot, you will see. And once you know this can be derived, right? It's almost immediate, so you don't have to memorize that. But if you can, do it. And once you're there, do it again, right? Contraction again. And that's showed up last time, right? Jordan pointed out that this is equal to, he said it was 6, but now we know how it is. So it is 2 times delta kk. Right? But we said delta kk is nothing like a trace, so that's the trace of the identity matrix. That's 3, so that's 6. Okay, so that's something you need. Any questions at this stage?
The trace is just the sum of the diagonal, right?
That's correct. So for example, if you have a matrix M, so for example, if you have a matrix M, right, later we'll represent a matrix like that. So this will be M11, M12. Let me just write 2-dimensional, 2, 1, 2, 2, right? And if I were to do MII, you notice that that's M11 plus M12, M22, that's nothing but the trace of M.
Okay.
Right, so that's in general true for any matrix. Right? Again, here mostly we will work with this Kronecker and Levi-Civita symbol, but this generalizes very easily for general matrices, especially if you had to do Dirac equation. That's the non-relativistic equation in quantum mechanics. That's mostly done with what is called Clifford algebra. All these are very handy in there. It becomes almost too tedious if you don't use this process. Even with this process, it's a little tedious, but very useful. Okay, so let me proceed. Okay, so what can we do with this? One straightforward thing is triple. This is called triple cross product, right? Triple cross product?
I think so.
Right, yeah. Why is it triple? 2, right? Suddenly I got confused. That 3 vectors, I suppose, but I was thinking double cross product, but no. I think it's called triple cross product. Okay. Okay, so that's cross product of 3, and you know this identity, right? If you are familiar with this, usually even so, since it is A crossed with this, you cannot have a component in the direction of A. Like whatever vector this is, it cannot have a direction, and it is perpendicular to A. So it is in a plane, right? So in that plane, it always can be written in terms of B and C. So there is a vector B here, if you want, and there is a vector C. So I think how we write this is B and C, right? And this is A dotted with C, and this is A A dotted with B. And this is minus. So it's often remembered as back cap, but it is also, so notice we have implicitly done a few things here. We have moved B with respect to A. So I've assumed that B commutes with A. So you cannot do this in quantum mechanics, right? Because in quantum mechanics, operators don't commute. Right? A momentum operator and position operator doesn't commute. So that's not allowed. So, or if these are operators, so it's often useful to write this as B, right? So this is C and and A, right? So this way I have not moved my components. But then how do I say that these are vectors? So you can use in components, right? That's so let's say this is J. This is J. So this is a mixed component. So this way I haven't moved things. Like you get in quantum mechanics, it's okay. And this will be A dotted with B. This is okay. There is no issues. Is that clear? Right? This is a dot product between A and C, which is written in terms of components. Okay, any confusions in there? Right? So make sure you get that. So yeah, extra credit, right? Extra credit problem. So this is a big so this is extra credit. Yeah, so we are in quantum mechanics. So this is in quantum mechanics. You have, what do you say? So this is L, so this is angular momentum. And these are the components of angular momentum. What is that equal to? Anyone remembers? If you commute to
LK, IH bar LK.
good, very good. So this comes out to be, it turns out to be, this is IH bar epsilon IJK LK. Okay. So the X component of angular momentum and Y component of angular momentum gives you the Z component of angular momentum. Right? So if I and J are fixed, so for example, L1, L2 is equal to IH bar. If I and J are 1 and 2, K has to be 3. Right? There is no other choice. So this is L3. Okay, so it's a cyclic property. The point is that they don't commute. What I wanted, the only quantity I wanted to take to realize is that these are not special, or these are not normal numbers. Like 3 times 4, if you were in classical mechanics, angular momentum is some 46 units of what's a unit of angular momentum, right? MVR, so kg meters per second or meter square per second. That's a number, and if you have 2 numbers, you cannot have this. So it requires quantum mechanics. The H bar has to be non-zero. So now the point is, what about 2 vectors, L cross L? What can you say about this? You have 2 vectors, and I take a cross product. What happens?
Well, are we saying they're the same vector?
Yes, exactly the same vector.
Well,
What's the cross product of 2 vectors?
If they're not orthogonal to each
not
other.
orthogonal to each other, so if they're the same vector, so that doesn't make sense to me, I guess.
It should be 0, right? I mean,
Should be 0, right?
one would expect it to be 0. At least that's a classical. Typically, that's what you would say, but not so in quantum mechanics. Okay. So let's see. So what is this equal to? We now have a better way of seeing this, right? This is equal to the ith component of this, right? Ith component of this is epsilon I j k Lj Lk,
Okay.
right? That's good. And now let me take the I equal to 1 component. Right? I equal to 1. This is 1. So if I is equal to 1, j and k has to be 2 or 3, right? So let's let me write this as jk Lj Lk. Oops. And that is 1, 2, 3 L2 L3 plus 1, 3, 2 L3 L2. Agree? And that's equal to 1, 2, 3 is 1. So that's L2 L3, and this is minus 1 actually. That's 0, right? Is that 0?
Can't be, right? You already told us it isn't.
It isn't, right? Why is it not?
Because they don't commute.
Because they don't commute, right? It is 0 in classical mechanics, right? Then I would have replaced this. These two cancel out. But not in quantum mechanics, because h bar is no more 0. This is actually I h bar 2, 3, 1, right? So this is L1. In fact, so here is the question. So this is an extra problem, right? So L cross L is equal to what? Okay. What is L cross? It's not 0. Apparently, the first component is L1, right? All right, IH bar equal to L1. Do the second component, do the third component, and find out what this is exactly equal to. So two vectors, cross product of two vectors is 0. It is 0, but only if the elements of a vector commute. So the components of a vector should commute. So that's a good thing to realize. And we also said that they are in a plane perpendicular to A. But what about the components? Like, where are our components coming in? How can we do this, right? So let's go back here and let's do this using our component notation. Can we verify this? So this is a vector. So this will have only one component. So that's the ith component. And that's equal to epsilon I j k times aj. Right? And the kth component of B cross C. Right? Any questions? Is that clear? So this is, again, I can do a cross product. So this is I j k. This is a j. Again, do k. I've already used I and j, so I have to use something else. So this I will use m n. Bm. Clear? That seems like too many indices, but these things collapse. Remember our identity. So this is the same as I j k. And now that these are components, right? These are components, all these are components, right? And assuming that I can move things around, but these are, see, even if we are in quantum mechanics, this is always 1. or 0. So I can move this through, right? Even if this was an operator, I can move 1 or a 0 through them. So this can come forward. So this is KMN. And before that, I swap these two, and then I swap these two. So 2 swappings doesn't allow, I can do it without a change of sign. That's M and K. So too many things I did in a single step. But hopefully,
So typically when I do this, I'm just wondering if it's acceptable. It wouldn't matter where, as long as you matched your non-free indices in the position, when you do the deltas, it'll come out the same.
it'll come out the same as far as K is in the same place, right? So K is here and K is at the end. If K is here and K is in between, then it doesn't work.
Because typically I always move that, so I would move K, it would be like Kij and then KMN.
That's correct. So for example, this is also equal to, I move it again, that's Kij. Move this also, KMS. Correct? Is that the question?
Yeah, that was the question. I was just making sure when you do the deltas, it didn't come out weird. I think it would come out the same.
It will come out the same. Check it out, right? Verify it, like let's say that's extra, another extra credit. Right? Or let's not keep that as an extra credit. Yeah, I don't want you guys to boggle down the too many extra credit. Okay? But yeah, it's a good exercise to check it. Okay, and you can even keep it in the center, and that's the same. So I, K, J, but it should be in the same place. And that's also the same. Okay, that helps, I suppose. Okay, but once we have this in this form, then replace this in terms of delta, Kronecker deltas. So this is IM JN minus IN JM. Again, typically, if you get very efficient at this, you can finish this off in 2 steps, but I'm doing this in many steps just to clarify things. It's actually just 2, after you get used to this, it is only 2 steps or 2 or 3 steps of the math. Now what do you, so let me expand this again. This is JN AJ BM CN minus of delta IN JM AJ BM CN. Okay. And now again, we start contracting. Whenever Kronecker delta comes in with a vector, this is like identity multiplying a vector. I can collapse this J. I can collapse this. Let me keep the J's. I like to collapse the M's. So let me collapse the M here, and let me collapse the M here. There's different ways of collapsing. I can also collapse J. That's perfectly fine. So that's equal to. So wherever I see an M, so this is AJ, BI, CJ. Minus of, again, do the same, M collapses, N collapses. So this is minus AJ, BJ, CI, which is exactly what we have on the second line on the board, right? Here, if I were to now write this as a vector, so the free index is I, right? So that becomes the vector. This is AJ, vector B, CJ minus A dotted with D times vector C. So So there's a dot product in here. It's easiest to write it like this. Sometimes textbooks write so AJ vector B CJ. Sometimes textbooks will write this as A dotted with B is in bracket and then C. There's lots of notation that you're saying that this dot is actually crossing across the brackets. I don't usually use this, so you don't have to worry about it. I typically avoid this. If I had to write it at all in this way, what I do is, at least on the board, it is easy to do. So this is actually I write that as a dot product between. But it's not convenient to show the dot product. Easiest I think is this. Right? Introduce the index notation in there. Okay, so that's.
Is it less confusing to just bring the same components together? So just write AJ, CJ, BI.
Oh, if you see, but that may not be allowed usually, right? So you are saying, oh, this is, why not write this as this, correct? That's your suggestion. Agreed?
The dot product between, yeah.
Right? But now you have moved B and C. In quantum mechanics, you cannot do that.
Okay.
Or for that matter, if you had a differential operator there, you cannot do that. Right? So there will be situations where you won't be able to do that.
Okay.
Right. So, for example, in electrodynamics, if this was a gradient operator, which we'll see almost by the end of this lecture, that you will have trouble doing this with gradient operators. Like in quantum mechanics, there are matrices, you cannot do that. In electrodynamics, it's often the gradient operator because it's a vector or differential operator. It cannot change its position. So we'll see that coming in soon. Okay. So that's a small chart. Okay, but before I reach that, let me do one more quick identity. Let's say, yeah, what is A cross B? This is correct. C cross D. You remember the identity, that's perfectly fine, but this is another place where the same identity comes in. Two vector products, right? So you will immediately say this is I and I. So this you would say is A cross B, I, and C cross D with I component. And that's the same as epsilon I j k a j b k, and the same thing again I m n c m e n. Clear? Do the same idea again, right? This time I can almost do it in my head. Oh, I write del del. So this is j m k n minus j n k m, and that is a j k c m d n. Okay. I don't even bother to interchange. I get quick that m has to be replaced with j. So this is a j e k c j and d k, right? Dot product between a and c, e and d, minus j and m. This is k c ck and dj. Right? Again, if you're allowed to move things around, so if they commute, right? So this is if commuting, if components commute. if components commute, then I can move things around. And I would say this is A dotted with C times B dotted with D, and minus of, so now it is A dotted with C, but now I'll do A dotted with D, right? That's a swap, that's how you typically remember, right? But this is not what we're interested in. We are interested in this case where it doesn't repeat. Or we'll come across situations where it doesn't commute. So then we got to keep that form. Don't proceed from there.
So just back a couple steps when you, yeah, well, the step below, whenever you change the components, you're saying that if you look at the delta expression above it, J, anywhere there's a J, it could be an M, or anywhere there's an M, it could be a J, right?
Because now it is dummy. I can replace J with M, J with Q. I can, so this is as well Q, right? Perfectly fine. Right? Any dummy variable.
Okay.
Right?
It's just, you can swap any of the two for that expression, right?
Sure. Good. Yeah, good point. Yeah. Any other comments, questions? Okay. Okay.
So
Yes.
I have a question.
Uh-huh.
So could you not simplify the second term anyway? Because BKCK,
Yeah, this is B dotted with C.
and then
Yes.
that's a scalar, so you can move it out?
No,
Okay.
because even if it's a scalar,
Mhm.
it can be an operator.
Okay.
Think of a differential d by dx, for example.
Mhm.
Right. So, for example, this so f of x, right, times d by dx. Right? This is a scalar in a sense, like in one dimension.
I see.
This is not the same as d by dx of f of x, because this could act on something, right? So think of it as acting on g, right? So this is no more this. So what is this equal to? So if I were to move this around, so I have to now be careful on what I'm acting. If it is acting only on this, that's not the same as this. Even if it is acting on both, it's not the same. So what is that equal to? So what you would do is this is equal to d by dx of both if you want, minus of I have to get the g or f out, right? This is df. Can they see what I'm writing?
Mhm.
Probably not. Ah, they can. Is that clear?
Mhm. So the best you can do is simplify to B, so
Dot.
AJ B dot C.
That's right. So it's this, for example, there are various tricks you can use now. So this is A, J, B. So this is, let me write that again. So this is DJ, right? So the question is, what is this equal to? This is surely AJ B dotted with C and DJ. Right. And you can actually get a little more clever if you, I mean, again, these are all just elegant ways of writing this. If you don't like this mixed stuff, here there is component, that's a vector. You can write this as a trace. This is a scalar, these two construct a matrix. Right? So in that sense, this is vector A, B dotted with C, and there is D. If that makes sense. Okay, so that's another, but that's, if you're used to reading these kind of things, then this is nice. But this is also correct. This is also correct, different context. But since we're doing indices, I stopped there. But yeah, that's how you can, one way. And then you're not moving things around. Good. Okay, so all this I said is because we want to talk about gradient of And all this should be useful for E&M, but your homework for this course is actually on gradient operator.
So one quick question, after you do the, let's say you have, let's say you do have a gradient in there, are you going to have to do differentiation by the product rule in order to?
Yeah, that's what I'm going to do right now. Give me a few minutes, probably to get you, I'll answer that question. Okay? Reasonable? Or actually, I won't be able to answer it immediately because I want to first motivate the gradient operator. So your question is, yeah, okay, so let me answer that right here. So the question is, okay, so cross product seems to have, so A, yeah, so, yeah, so A cross B cross C has a distribution law, right? So this is distributes, I'm saying. In the sense of a, let's say, B times AI CI minus A dotted with B times C. Agreed? So this is sort of a distribution rule for cross product. So whenever A operates on two vectors, this is how it distributes, right? If there was a gradient operator, right, derivative also distributes, right, independently. Right. We also have a distribution of derivatives. So this is df by dx times g plus f times. Great. So this quantity, so maybe I should go back and write this as A, right? So if I have a del cross B cross C, right? This derivative, because it is a vector, it has a distribution of this kind. Because it's a differential operator, it has a distribution of this kind. So it has 4 terms. So this will have 4 terms. Not 2, not this 2, but both together it is 4. 2 times 2, it is 4 terms. Okay. But let's come back to that. I haven't really, I first want to talk about the gradient operator a little, and then I'll come back to that. But I may not have time for it today, but we will address this probably tomorrow, I guess, in the E&M class.
Okay.
Since it's kind of fun. I'm doing it in both classes, partly here, partly there. Since many of us are there, it's okay. Okay, but it should at least answer your question, at least as far as insight goes.
Yeah, it actually answers the. Yeah, it actually does. Yeah.
And it's good to realize that. And I hope even those, even though others realize that there's this 4 terms that comes in, and but I may not be able to address that in the next 20 minutes. Okay. Okay, so I kept repeating that we are doing all this because I want to talk about gradient operator. Electromagnetism deals with the gradient operator a lot. And so gradient operator is just written as this. Like any vector, it has a meaning of itself. I don't have to really go into any particular coordinate system. A gradient operator should have a meaning in itself. And let's say that this is acting on a function which is there everywhere at, as well as scalar field, right? So maybe I should point this out. So this is a scalar field in the sense that at every point there is a value, right? So this is called a scalar field. And this will be a vector field, like electric field, for example. So at every point in space, you associate a vector. That's a vector field. At every point in space, you associate a number. That's a scalar field. And you can immediately go and say, there is Eij of x. This will be a tensor field. Right. Are these two the same? No, because a vector cannot be equal to a tensor. There's no way it can be equal. So they're not the same. Even though I use the same letter, doesn't mean that it needs to be the same at all. Okay. Give an example of a scalar field.
Temperature.
Yeah.
Temperature, yeah, temperature in a room. That's a scalar field. Very good. Electric field is an example of a vector field. And tensor field. Have you come across any tensor field by any chance? Field. Yeah. Begin with the tensor. Probably not, but have you guys seen
A
any?
gravitational field be a tensor field?
In Einstein's equation, yes, but you haven't seen it, right? Probably not. Yeah, that's correct. In gravitational, what is this? Einstein's equation, the metric is a tensor. But you haven't seen that. Where else do you see tensors? Moment of inertia is a tensor, but it's not a tensor field, right? It's just 9 components, so it's not a tensor field. It is just a tensor. Tensor field, I guess you will see it in ENM, and that's the best I can say. Yeah, we will see this in 3 weeks, I think, as far as physical quantity goes. I think we have not seen a tensor field before, I guess. Yeah, I don't think so. Yeah, I don't. Okay, so if you're given a function f of x, what is the interpretation of the gradient of the function? So this is called gradient, right? So first let me some terminology, right? When it acts on a scalar, this is called the gradient of f, right? If it acts on a vector field, now notice, so that we, yeah, so this is a function, right? So now these are 2 vectors coming together, so there can be a dot product or a cross product, right? So there's a dot product and there's a cross product. So this will be the divergence of E. And this is the curl of E. And I'm assuming that you have seen these terminologies in some course on vector calculus, right? So I'm not going into the details of what's that construction. Here I wanted to talk about a little motivation of what that is about. Like I want to get a physical picture of what this is, and very vague. As we go, we will make this better and better. That's if you want, the whole course is about getting a feel for these quantities. Let's say what's the gradient? Right? So what's the interpretation of this? Right? There is a function f, and there is a gradient of that. What comes to your mind?
Partials.
Correct, partial, but I want a physical insight. That is algebraic. Yes, that's so. What maybe I should write that. What is it? Equal to that's partial. Yeah, that's okay. That's great. So this is what you mean, right? So this is f plus j plus k. And this exists at every point in space, so you've built a vector out of it. But what is that equal to? Suppose I give you your function f. What is that equal to? So, yes.
If I remember right, it means that the magnitude of the function in a very certain point at every point in the field. Is that right?
Tell that again. Maybe I didn't capture it completely. Magnitude of
the gradient operator gives us the magnitude of the function at every point that we.
no, magnitude of the function.
No.
The slope?
Tell that again.
The slope?
The slope, usually if it was a one-dimensional function, that's a slope. In this case, like, what do you mean by a slope of a function, right? Let's say if you're in 2 dimensions, let's say, right?
I'm just thinking straight physically, if the gradient of something is like the slope of that surface.
Rate of change, is it? Rate of change?
Rate of change of what? Like there are
Of the
3 rate
function.
of changes there. There is 3 rate of changes, right? This is rate of change of f with x.
At every component, I mean.
Yeah, that's correct. So that's that's okay. Yeah, rate of change of 3 of the function f in 3 different directions, correct? That's okay. So for example, let's take an example, right? Let's say I want to do x squared plus y squared plus z squared. Okay, so that's a function f. Let me define it this way. F is equal to f of vector x, right? Is equal to this, right? And if this was before that, remember, what is this equal to? How do you see this? That's a constant a square. What is that? Is this familiar equation?
Sphere.
Yeah, equation of a sphere, right? If I were to have points x, y, z such that x squared plus y squared plus z squared is equal to r squared, that's a surface of a sphere. That's a points on the surface of a sphere. Agree? Now, with that in mind, if I were to do gradient of f, what is that equal to? If I were to ask it that way. It's really inconvenient with the mask. Go ahead and operate it, maybe. It's not very hard to do it, right? Just do it algebraically and then you'll get an answer and then see what that is. So let's do it so for example, if I were to do I hat times the derivative of f, right? With respect to x, it acts only on this. So it is 2 times x, correct? Plus j hat times 2 times y plus z hat times 2k, k hat times 2 times z. So that's equal to 2 times vector r. So, and vector r has this feature that this is the sphere, right? The vector r is perpendicular to that.
You get a vector field?
You do get a vector field, but more than that, the point is that think of this as a surface. If you have a function, a scalar field for a constant. That scalar field equal to constant is a surface. Like think of in your room, think of all the points which have the same temperature. Right? That will form a surface. If it's a continuous scalar field, then it will be a surface. It might be a complicated surface. So in this room, ask all the points that have 73 degree Fahrenheit. Right? That will form a surface. And then you take the gradient of that. At every point on the surface, you get the normal. So what is the gradient of a function? It is normal to that function equal to a constant. Set that function equal to a constant, you get a surface. It's perpendicular to that surface. Is that clear what I said?
I think so.
Okay. So on a surface, it is perpendicular. So let's, so this is what your homework is all about. So let's, so you have to do this in spherical geometry. I will do this in the simpler geometry of 2 dimensions, right? Let's say polar coordinates, like cylindrical polar coordinates, right? And there, what you do is you have a magnitude of a vector and the direction, correct? How do you do this? Let's say you have r, vector r is equal to xi plus yj. And your x is equal to r cosine theta, y is equal to r sine theta. And you can also say x squared plus y squared is equal to r squared, and theta is equal to tan inverse of y over x. What does all this mean? Its coordinates have to do with coordinating a point on a plane. Right? So then you ask, if I want to mark every point on this plane, I need a set of surfaces. I'm doing 2 dimensions, so it becomes the lines. Right? So there's a set of lines. This is y equal to a constant. Notice this gradient I'm going to talk about, right? So y is equal to a constant. And there is another set of lines, curves. That's x equal to a constant. Right? That's one way of doing this. I need my coordinates, so I say, oh, what is my coordinate here or vector, unit vector? I will do gradient of x equal to a constant. X equal to a constant will give me the gradient perpendicular to x equal to, see these are x equal to constant surfaces. Gradient will be perpendicular to that. That will be perpendicular. Right. So this will be, and then divided by its magnitude, if you're afraid that it will come out not a unit vector. This is defined to be your j hat direction. Is that visually clear? Right, there are constant x surfaces. Gradient of that gives me my j. Same thing, do it with gradient of y over, that's your I hat. So that's your definition. If you want, this is how you define it. Right? These 3 lines means that this is how you define your unit vector. But now let's do in cylindrical polar coordinates. This is not the only way you can make a coordinate on a plane. I can do it another way, that is by having circles. And
I have a question.
yes, go ahead.
So what you're doing, I'm a little confused because it just looks like a total derivative to me.
Total derivative.
Like a total derivative looks like a gradient now. The sum of the partials.
No, that's not a vector. Remember, total derivative. I think what you mean is, if I'm not just, so if you have f of x of t, right? And y of t, right? Then total derivative is partial derivative, and that could be t also here, plus dx by dt, d by dx of f, right? Is this what you mean?
Yeah.
But that can be written as a gradient, but that's not the gradient itself. For example, you would write this as d by dt plus this is velocity if you want dx, if this is velocity. So this is, I would say this is dx by dt, if this is dependent only on t, dotted with gradient of f. Is that what you have in mind? Probably. But that's not the gradient operator first. The gradient operator is not the total derivative. Does that help? Is that what you had in mind?
I guess it just depends on the surface. Or
No. Surface, see, this has this implicit p in it. Only then you can do this total. The difference between total derivative and partial derivative comes in only when there is an implicit variable inside. Here, I'm just talking about a scalar field, a surface actually. And if I were to operate a gradient operator on it, what does it mean? I'm saying that it is perpendicular to that surface.
okay.
Does that help?
Yeah.
I hope I didn't confuse. It's 2 minutes past, but let me take a few more minutes because this is helpful for your homework. Now, notice if you want to make coordinates on a plane, one way is to crisscross the lines. This will be your north and east, right? You go certain direction north and go to certain direction east. But you can also do it in another way. Make circles, and then you have half lines. This also is a way of making coordinates. These are basically cylindrical coordinates. But now I want what are the unit vectors in this? And I would say, oh, my unit vectors to this are perpendicular to the surface. And that will be gradient, two-dimensional gradient now. These are circles, more specifically square root of x squared plus y squared, right? That's my surface of a circle. I get two-dimensional surface of a curve, and then divided by magnitude of that. And that will be your r hat. Okay. Visually, that's very clear. In fact, if you literally do this, you will get it. And that's your homework. You have to actually do this in 3 dimensions. It's a little work in the sense there are some derivatives, but it comes out exactly r hat. And you can actually do this for these lines also, right? Lines are also surface. Now notice the perpendicular to this line is this way. Right? That's your phi hat, like perpendicular to these lines. And that will be equal to gradient of, let's call this phi, right? Not theta. Let me call this phi. So that's tan inverse of y over x divided by the magnitude of that. Okay. So derivative of tan inverse, look it up. You should be able to do that. I usually do this as an example here, but I think I'll just make you guys get home. Ask me if you have troubles in doing that. Okay. So in your homework, what you have to do this is for a sphere. So a sphere is built out of spheres, cones, and then cylinders. Right? What is sphere made up of? Constant r. R is equal to a constant. Like those are spheres. Theta is equal to a constant. Those are cones. These are cones. These are spheres. And phi is equal to a constant. Those are cylinders. So for example, if you have a sphere, that's your cone, that's constant angle. And then for phi, you will cut this down. So if every point in a three-dimensional space can be coordinated using a sphere, a cone, and cylinder. I went through too quickly there. Hopefully, you guys will be able to manage the homework. Okay. Any questions?
Yeah, what's the gradient?
What's the gradient?
Yeah.
That's the
Can
question?
you ask this?
Tell that again?
You asked us what's the gradient. So I'm asking you, what is the gradient? What's the definition that you would get by?
Oh, gradient. Okay, so what is the gradient? Gradient is a normal to a surface. Whenever you have a gradient in mind, it is normal to a surface. But then you ask, usually you take gradient of a function. So you set function equal to a constant. So this is the gradient of f. Oh, you cannot see that. Okay. But here is what the answer is. Okay, gradient of f is equal to gradient of f minus a constant. Remember, gradient of a constant is 0, so I can always introduce that. Now this has a meaning. F is equal to a constant is a surface. Right?
Mm-hmm.
A function being a constant is a surface. So gradient is a normal to that surface. And it could be any so there's a class of normal vectors that comes out. Like r hat again, right? R hat is perpendicular to a lots of so you put a constant, whichever constant you take, that's okay. Does that answer?
Yes.
Can you summarize that?
Yeah. It does.
Yeah, think about it, and the homework problem hopefully will help you.
Excuse me, doctor. I'd like to thank you very much about the example you gave it about of the sphere x squared plus y squared. That really visualized it very well.
Good.
Thank you.
Good. Okay, thanks. Yeah. Okay. I'm glad. Yeah. Yeah. Think about it. Yeah. I'm sure. Yeah. Okay. So try to do the homework. So there are three. Try to imagine the three surfaces of a sphere. It helps. Okay. Okay. Good. Any more comments, questions?
I don't think so.
Okay. Good. Michael.
I think I'm good.
Good. Okay. Alia, you guys are quiet a little. Yeah. Feel free to ask questions. Yeah. Okay. I think Jordan and others are probably they've been with me for some time. They feel more comfortable, I suppose. So feel free to ask questions. Okay. Good. Thank you. Okay.
You.
Enjoy, guys.
Hey guys.
Yeah. Everyone log out and then.
Oh, one quick question.
Yeah, sure.
Last semester we talked about like a place where we could go to talk. Is that still a thing, or is that just?
That is still existing, actually. That same thing. I
It's
think
not using
Moses helped set it up. It is still. It should be still existing. Why don't you guys try that out?
Yeah, we should do that.
Yeah, we should do that for if anybody has like.
So what is? I think some left. I think Michael left, right? Or Mike one color left. So the point is, there is. What was the name of that? Do you remember?
It was just the
Oh, you need the
lounge.
number, right? You had to give the number.
Oh, the
Meeting ID.
meeting ID number?
Yeah.
I could look it up.
So how about Moses will send something, the
Yeah.
password and.
Sure, I'll send it out to the whole department, I guess. Basically, it's just a virtual, it's Shadjesh's account.
Yeah.
but a place for us to meet, just online.
Sure.
Okay, it was something we did over the summer, kind of like as a way to just like hang out in a lounge, since we can't hang out in the physical lounge, just have a virtual lounge, so.
So for example, I think the idea is that you can use it for working on homework and other things.
Mhm.
I think that was the goal. But in the summer, there were no homework, so it was never used. So it's sort of was a failure in the summer, but I think maybe now it might be a useful. Yeah, let's see how much it gets used. If it's not used, no big deal. It's
Sure.
just yeah.
Sure.
Okay. Does that answer? So Moses will send you guys the information. I do remember the password, but maybe we should make the password simpler, right?
I don't know. I mean, it's still IH bar, right?
Yeah, it's actually it's easier. Okay, Moses will send you that.
Okay,
Right.
thank you. Bye-bye.
Bye-bye. Thank you. Bye, Alia.